Well, seminar. I'm filling in for Sarah and would like to introduce Kathryn Sellwood. She's been here at the APHEX meeting that we've had this last few days and agreed to stay on and give a seminar, which is great. Kathryn comes to us from University of Miami and NOAA, CIMAS, I think it's called, CIMAS, yeah. And has been in Miami for all of her professional career. She, prior to being at NOAA, where she's been at the HRD Hurricane
Research Division.
Hurricane Research Facility for 20 years. Prior to that, she was at the University of Miami Erasmus, where she did her undergraduate and graduate work. And she's got lots of awards and publications on all sorts of aspects of hurricane work. But one thing that when I was reading about her that I really wanted to bring up was a quote that's on her webpage. And she said that she read, on her webpage, she says, "I read that meteorologists should have math and science aptitude and be a bit crazy." And I thought that was an awesome quote. So with that, please welcome Kathryn.
Okay. Awesome. So, thank you so much. I'm really happy and grateful to be here. And so, obviously, since it coincides with the AVAPS meeting, this talk is going to be dropsonde oriented. And so, we're going to talk about some of the science and observations using the dropsondes from the 2024 NOAA HRD Hurricane Field Program. And so, I've just listed some of the authors that have contributed to this talk. So we had a super busy year last year. Lots of storms, lots of research and operational flights. Almost 1,500 dropsondes in total just from NOAA. Another over 2,000 from the Air Force. And so here's just a breakdown by storm, by aircraft. And it just shows which storms also had concurrent ocean measurements. And then we also had some experimental dropsonde streamsondes that we released in conjunction with the operational dropsondes. And so because we were flying so much last year, so you can also see the flight tracks there all superimposed. So we had the opportunity to do what we call flight modules. So these are compact little experiments that we tack on to the operational flight paths. And these are to study specific atmospheric phenomena and processes. And so I'm just going to go over a few of those to start with. So last year we did a number of these microphysics spirals. So these are a module designed specifically to get a better understanding of the number and concentration of microphysical particles in the atmosphere in a hurricane or tropical cyclone. And so you can see a couple of flight tracks there, so how they add them onto the flight track. On the top left there, that's what the flight pattern of the spiral looks like. It's color-coded by height. And so what we do is we target a region of stratiform precipitation outside of the radius of maximum winds. Then the aircraft spirals down as low as it can safely go. We shoot for about 500 meters above the surface. And it's measuring the hydrometeors with microphysics probes, and it also has the tail Doppler radar to get a more 3D look at these things. And so then once it's gotten as low as they can, the aircraft spirals back up through the freezing level, so it's getting the changes in the particles. And once it reaches the top of the spiral, we release a dropsonde, and this gets the thermodynamic environment that goes with those microphysics observations. And so that's just what one of the temperature humidity soundings looks like for a spiral in Beryl. Okay, we also wanted to look at the impact of island wakes on the atmosphere, so downstream from island chains. And so we weren't out there that much this year, but we did have an opportunity during the Magpie campaign to sample downstream from the Antilles. So what we do is, so you can see in the satellite image that there's much less convection on the lee side of the islands. And so basically we go parallel and capture that wake and release a number of dropsondes in series to kind of see how the atmosphere is varying along there. And those are just some of the soundings that we collected. Another thing we wanted to look at was we had this Eye-eyewall mixing module. And so we want to know if we can identify meso or mesoscale vortices, type I, in the atmosphere, and see if we can identify, of course, we get a better idea of the gradients across the eye and the eye wall. And so what we do is a series of rapid release dropsondes. We start outside the flight level radius of maximum winds, and we release a number of dropsondes until we're inward of the surface RMW. And then you can see how the winds and the thermodynamics are changing as you go inward. And so here's a sonde sequence from Hurricane Helene, where the rightmost sounding is from the center. So you can see how that environment is changing. This is a sequence from Hurricane Beryl. So the trajectories there are on the lower left. And so if you look at that green sonde, which is the outermost dropsonde, you have temperature and vertical velocity on top, wind speed and humidity on the bottom. And you notice that in the mid-levels, that green dropsonde is a little warmer, a little drier. And that's giving us some indication that there is some sort of exchange across of that drier air in the center of the storm with that outermost dropsonde. So that's giving an idea that there is some sense of mixing going on between those two regions. Okay, another module we do is this favorable air mass module. So here, this is in Hurricane Beryl. You can sort of see this dry moat where it seems that there may be some drier mid-latitude air getting into Beryl. So what we do is we do a box pattern around that, and we release a number of dropsondes, and we also sample with the tail Doppler radar. And this gives us an idea of how that dry air might be getting entrained into the system, and also how it might be being repelled by the storm. And so that just gives us a little more insight into the dynamics that are going on in this case. And that provides some information about whether or not this storm has the potential to continue to intensify. Another experiment we did is fairly often last year is we coordinated with ocean assets. And so what we do is try and adjust the flight path so we get as close as possible to a sail drone or an ocean glider, and then time the release of a dropsonde so it gets as close as possible. And we had a number of those. Partially, the goal is to validate the observations from these ocean assets, but ideally we want to sort of get at that connection between the ocean and the atmosphere. And so the figure on the bottom there, you can see where it's circled, you have wind speed values from multiple different instruments. So we have the SFMR, down we're looking K-band radar, the triangle is the sail drone, and then the circles are dropsondes. And you can see that those are all pretty much in agreement. Okay, and we are continuing to add to this database of sail drone dropsonde combinations. And so this is just, I believe, wind speed and pressure comparisons between those combo drops. And these are all dropsondes that were within 50 kilometers of the sail drone. And so you can see there's pretty much a good agreement between them. And obviously the outliers are because we are in such a turbulent and changing environment. Okay, we also do comparisons with the gliders, which actually submerge and take ocean profiles. And so there's a list of the number of combos that we have to date and their distance from the closest dropsonde. And so the figure up top just shows a sounding of believe it's pressure, wind speed, and wind direction from the dropsonde, and then the profile of temperature, salinity, and density from the ocean glider. So that's, ideally, we want to get that full picture all the way down through the atmosphere, through the mixed layer of the ocean. We also coordinate with other agencies. So ONR does these sensitivity tests, and we had an opportunity in Hurricane Ernesto to sample across a region that they had identified as being particularly important for the downstream forecasts. So what we did was we added some extra dropsondes along that north leg of the flight pattern and to sample this region, and hopefully the ingestion of that data would lead to improvements in their forecasts. And so just the profiles from those soundings are shown above. We also coordinate with the Tropics satellite mission. And so the Tropics constellation, it's currently 3 CubeSats. It's like low Earth orbit, so very rapid return time. And so we tried to deploy G4 dropsondes anytime we could within 30 minutes of a satellite overpass, and particularly targeting moisture gradients in the environment and near the inner core. And so just shown here are some comparisons between the tropics water vapor and that measured by the dropsondes. And so this is really ongoing research, and they're continuing to do comparisons and data impact studies with the tropics data. This is a really cool figure that Sim Aperson came up with. So what he did was he plotted dropsonde profiles. This is wind speed collected during Hurricane Milton, when Milton was a major hurricane. And it's on the same height scale as the Miami coastal high rises. And so you can see what the impact at each height would be if a storm like Milton were to come ashore in Miami. Okay, recently published was a very comprehensive multi-year dropsonde impact assessment. And so they did this within the basin scale HWRF because it has multiple moving nests where you can get higher resolution around multiple storms. And they just looked at the impact of dropsondes within 500 kilometers of the storms. And so the main takeaway is that when you use more advanced data assimilation techniques, specifically using a model consistent ensemble to estimate your covariances, you can get significant impacts in track intensity and size metrics. So green is improvement, red is degradation. And you can see that with the less advanced DA, which is really using the GFS ensemble, you're not quite getting those results. So how you assimilate the data is very important. And on the right, you can just see that that impact by TC category is similar for both tropical storms and hurricanes. And another takeaway from this assessment was that the dropsondes in the inner core, so within 75 kilometers of the center, really had the greatest impact. So whereas overall you were seeing maybe 5% improvement, you're seeing 10 to 15% improvement in both track and intensity. And you're even getting improvement on the global model through this. So another paper looked at the impact of adding an inner circumnavigation pattern to the G4. Typically, they had just done one sort of farther away from the storm, but they saw that adding this inner circumnav, so this is on the right there is the new flight pattern, and the track forecast error is in the center there, and so the red is when you add that inner circumnav. So you can see significant improvement to the track forecasts at all forecast lead times. And over all the cases, so this is like a 6-year assessment that had that inner circumnav. You can see fairly good improvement in track, intensity, and size metrics from left to right there. This is some work that I'm doing. So traditionally, dropsondes have been transmitted and assimilated as temp drop messages, which typically contain only about 20 vertical levels. But more recently, we've been sending the 1 second resolution buffer data, which has closer to 1,000 levels in it. And we'd like to, it has, since we have a lot more data, we'd like to start figuring out how best to use this. And hopefully all the NOAA aircraft are transmitting buffer, and hopefully in the next year or so, the Air Force will be as well. So we don't want to just throw all this new data into the model at once. So we were looking at methods of super-obbing the data. And after some initial testing of different methods, it seemed like super-obbing along the profile to standard height levels was the best way to go. So we started with 150-meter height level super-obs. And so up top, I'm just showing the vertical distribution of the observations, super-obbing that way. So here we have leftmost from buffer and from temp drop. And that's the first two figures are for when there's only P3 and Air Force data available, so only low-level data available. And you can see that with the buffer, it's a lot more evenly distributed, and we have about twice as many observations. And then the two figures on the right are, again, the buffer and the temp drop, but this is when we also have G4 data available. And so you can really see where the temp drop is much more concentrated towards the surface. And so I've been running multiple storms from 2021 to 2024. So far we've completed Ida, Fiona, Ian, Franklin, and Lee. And so we're noticing the first takeaway is good. We're not hurting the forecast by using the buffer data, but we're actually getting fairly good track and intensity improvements. For MSLP and size metrics, the impact's pretty neutral, but it seems like so far that this approach is a valid one. And so we're just continuing to add cases to this and just build on this database. And then this was just one approach, doing the 150-meter height levels. So we identified a case for Hurricane Francine where we have a lot of cycles that have recon data, but it's fairly short-lived storm so that we can run this case over and over again. And so we want to test different ways of super-obbing the data, maybe get more height levels in the surface near the boundary layer, just test to see, what the limit is on how many observations we can assimilate before we start going the other way and degrading the forecasts. And so we're also going to look at assimilating dropsondes in conjunction with other recon data and other methods of super-obbing some of the other recon data like the TDR. And so, as I said, we had dropped some of these experimental Streamsondes this year. And so they're a very lightweight dropsonde, and you can release many of these at the same time. So you get a lot higher horizontal density between the slower fall speed and just the fact that you can release more of them. And so the trajectories there on the right are just a series of 4 Streamsondes. And then there's a close-up that's a 3 by 3 kilometer box. And so you can see that there are places where those dropsonde profiles are less than, say, like a quarter of a kilometer apart. And so the super-obbing along the profile might not be the best approach when you have this distribution of data. So it may be better to do super-obs in a batch so that you're more on sort of a horizontal grid. So this is some other work that we're going to be starting very soon. We're also looking at how better to estimate surface wind speeds. And so typically what's used in operations is this reduction from the average of the wind speeds over the lowest 150 meters of the dropsonde. And they developed an empirical reduction factor, which is shown in this black line. But the blue and the red dots are the actual reduction factors looking at the individual dropsondes, their 150 meter average, and their surface value. So you can see there's huge spread around that reduction factor. So we'd really like to come up with something a little better. And so on the right there, we have some profiles from the IRAP, which is a downward-looking K-band radar that gets really good resolution in the boundary layer. And our approach is going to be to first figure out how to stratify these profiles, probably by quadrant and storm strength, and to see if we can identify some basic shapes of profiles and use those standard profile shapes to do a better surface wind reduction. Okay, so we've kind of gone over how we're observing. So this part is going to just show you some of the more interesting observations that we collected. So dropsondes are used in real time for, NHC producing their forecasts and advisories and estimating what the maximum intensity at the time might be. But they also look at them after the fact to write their hurricane reports. And in that process, they came up with a couple of dropsondes that turned out to be kind of crucial to estimating how strong, in this case, Hurricane Beryl. They weren't sure whether the maximum intensity should be 140 or 145 knots. And they really focused in on this one dropsonde, which this is the data at the very bottom of that sounding as we're trying to process it. And you can see that there are some inconsistencies in the pressure. There's some data dropouts. There's some flag data here that looks like it might be reasonable. And so in real time, we erred on the side of caution and set the end of the sounding up higher and said it didn't reach the surface. We don't know what happened at the bottom. So this got sent out to a number of people that have a lot of expertise in dropsondes. And we said, what would happen? We could end here. This is where the satellite drops out. We could end down a little further down because it looks like the pressure values and the other data look pretty good, but obviously at the very bottom, it looks pretty bad. And so the result is that depending on where you choose the end time and whether you flag and unflag data, you get a very different surface value. So the surface wind speed varies from 126 knots at 10 meters to 183 knots at 15 meters. And then you can see that there's a difference also in that average over the lowest 150 meters, which usually is considered to be a lot more stable value to use. And the difference in that is really related to where the midpoint height of that layer is calculated. And of course, in these dropsondes, you can see from the sounding, you can see that gap, and you can see a jump in temperature. So just everything about this made it really difficult. So in the end, we ended up in agreement that this middle value, which resulted in 143 knot surface wind, was the correct value. But we went back and forth on this for quite a while. And we had a similar situation in Hurricane Milton. And an additional factor in this, there was a lot of wind speed data flagged near the surface that was very consistent with the rest of the data. It looked fine. And so do we keep it? Or do we trust that the automatic QC threw out the data correctly? And again, the pressure was really fluctuating quite a bit towards the bottom of the sounding. So again, it's like, do we end it here? Do we end it there? Do we keep the data? Do we not? And again, we get this wide range of solutions depending on what we do. So our surface winds varied from 109 to 133 knots. And again, you get that variability in the lowest 150 meters as well. So in this one, what we ended up doing was taking what was sent operationally, which gave a surface value of 122 knots. However, we were not able to reproduce that on the ground, so I have no idea how that was done. But it seemed consistent with what we were finding. And so this is just to demonstrate a little bit more about how the midpoint height of that 150 meter average can have so much variability. So this, the green line is wind speed, and this vertical dotted line is where the midpoint of the 150 meter average is calculated. So you can see if that midpoint was a little closer to the surface, that you would be averaging over much higher values, or if it was a little bit higher up, you'd be averaging over much lower values. And that just sort of gives you an idea of where that variability is coming from. So another thing we looked at was, since the WL 150 is based on geopotential height, and say we really aren't sure about the surface, can we use the GPS height? And so this is an experiment that Holger did, where he just put some dropsondes up on the roof and recorded the GPS altitude. And although they were just sitting up there, they weren't doing anything, that altitude was fluctuating on the order of about 10 meters. So that gives you an idea of the uncertainty in that value as well. And so another thing we saw last year was there are a lot of these dropsondes with this rapid temperature increase near the surface. And this is something we'd really never seen before. It didn't look realistic. And I think for the first couple flights, we were starting to throwing out that surface data. But going back and looking at it, it seems like it's actually good data. And the reason for that is if you look at the SST analyses below and where those dropsondes are located, you have a much warmer ocean than atmosphere, and so the atmosphere is rapidly adjusting to that warmer ocean near the surface. And so you get this hockey stick looking profile. And so these weren't the only extreme thermodynamic observations we had. So these, the top is from Hurricane Milton, Beryl, and the Magpie experiment, where you have these extremely low humidities in the upper levels, so very dry layers, even though some of these were very strong storms at the time. And below you can see these extremely warm soundings. So the maximum temperature in this leftmost sounding is about 90 Fahrenheit. And we weren't sure whether this was real or not. But my colleague Sim Aberson went back and found out that these were not even the warmest soundings that we've measured. We've actually seen warmer upper atmospheric soundings in the 2010s. So these are actually good data. We also had some extreme vertical winds. So this is a sounding from, I believe this is Hurricane Beryl. And so you can see this crazy shape in the temperature profile. That's because the sonde was actually lifted upwards. The vertical wind speed here is to the very right. So you had vertical updrafts on the order of 20 meters per second. And we also had very strong horizontal winds. So this sonde was ejected more than halfway around the eye, which actually might even be a record for the longest sonde trajectory. And so here's just an example of some of the extreme horizontal winds measured. We have surface wind speeds in excess of 140 knots. And I just showed the trajectory from this one Beryl sonde, which also went halfway around the storm. And so we really flew some unusually strong storms last year. And just for people that are using the data for their research, there is some bad data that did make it through the QC process. The people processing the dropsondes are under a lot of pressure. It's very difficult flight. atmosphere, so you're bouncing around and you might not catch everything. And so these are some of the things that actually made it through. So you had a lot of bad humidity data that made it through at low levels and also at the top of the soundings, as well as some data that appears to be after the sonde is actually splashed in the ocean. This is probably not as easy to see as I would like, but one thing we're working on is improving the visualization for the Hurricane Center. So what they're able to see right now is strictly the data points from the temp drop, which is on the left, and I'm sorry, that should be a little bit bigger. But what we'd like to provide to them is the figure on the right. So we're working towards getting that buffer data into their AWIPS visualization system so they can really get a better idea of what is going on in the atmosphere. And so this is a visualization tool that a intern of Sim Aberson created. So this is like a 4D visualization where you can look at multiple soundings at the same time. On the bottom right is plotted in terms of time. And so the diagonal line indicates the same time in each dropsonde. And so you can see whether features that you're seeing are actually the same in all the dropsondes. So in this case, the theta E minima can coincide in time, but there's really no strong signal in the wind components. And so you can do any number of dropsondes. You can rotate the display in all directions. You can zoom in and out. You can also, mouse over and display individual values. And so this is going to prove to be a really interesting research tool. We can also include other platforms like SUAS and hopefully Streamsonde within this. And we were hoping to be able to do a live demo. I do not have this set up on my computer, so that is a broken promise. But if anyone would like to see this further, please get a hold of myself or Sim Aberson. And that is what I have for today. Thank you.
Great. Thank you very much, Kathryn. You're doing a lot of things here with those data. Questions?
Kathryn, thanks for this very encompassing talk. You obviously do a lot of dropsondes. And actually just a comment I admire you, and it's a big challenge for you to document and write all of this up because there's such a variety of things. My question was actually very early on, you showed this one profile with a microphysics probe with a plane spiraled upward. And I was surprised that you used the dropsonde then for the thermodynamics when you have the aircraft as well. Did you compare the aircraft thermodynamics and the dropsonde thermodynamics in that spiral? And what came out of it?
I don't know if anyone's done that. That would be pretty simple to do. At least, you'd at least get they wouldn't be exactly concurrent as far as the locations, but they should be pretty similar.
As close as you can probably do it, in this type of a scenario.
So I'm not sure how the banking angle of the aircraft might affect the sensors.
Mm-hmm.
But that seems like it's something that would be pretty easy to look at.
And the data, the microphysics data, are they easily available?
I have been trying to locate those, so I'm not sure how they're, where they are located, but I believe that there's quite a bit of post-processing required for that data.
I have a question. You talked about super obbing a few times, and I actually didn't quite understand what that was. Do you mind just
Sure.
explaining that?
So super obbing is if you have a large quantity of data and you want to have something that's more representative to use in the model, there are a number of ways you can do it. You can either set up a model grid and interpolate that data onto that grid, or you can do averages in time or space. But what you're basically trying to do is, rather than thinning the data where you're just like picking out the one bit of data that's closest to your grid, you're trying to get something that should be most representative of that grid point, looking at all the data. And so the way I'm doing it is pretty much, because we have such high resolution data, I'm just looking within, say, 15 hectopascals, or just a few, I don't know, I think I have plus or minus like 25 meters. But it is essentially an average. And it could be weighted or not.
More questions?
Excuse me.
Thanks. Sorry, Kathryn. You showed another slide where you looked at this dry air intrusion and did a box pattern around it. On the flight track, let's see, right there. It looked like you dropped sondes only in that rain band or outer band where there was, but not in the actual dry air intrusion. Why did you drop sondes all around the box?
So,
or did I mess up something?
they ended up being, you do get all four corners of the box. I think there was a sonde that failed, like in that northeast corner. But it's a little misleading because we kind of tried to put the flight path over like the nearest satellite image. So what we're seeing on the plane may not be exactly what you're seeing in the satellite image.
Oh, okay. Yeah, of course.
Remember,
yes.
we're flying at like 10,000 feet.
Yeah, of course. Got it. Thanks.
We have an online question from Jun Kong K. And it says, thank you for your great presentation. Can you tell me more about how you calculated the sensitive area? Is it using an adjoint model from your own model? Is it including physics processes?
Okay, so that's a tool that was created at NRL. They used their COAMPS model, and let me look and see if I have what their verification metrics are. So it looks like they're looking at some sort of a moisture-related sensitivity. So I think they look at different variables, but in this case, I think the storm was interacting with a cold front, and there was dry air intrusion from the continent. So that moisture verification variable was what was really standing out as being the most sensitive. And the green, let me show the green box there, so that's where they are trying to improve a 24-hour forecast for. So their observations in the red and blue areas, if you observe there, then in 24 hours, you're hoping to improve the forecast in that green box. And that's where their technique is saying that you should observe. But there are multiple different products to doing this, but most of them are based on an ensemble of forecasts.
And can I add to that? Is that done prior to the flight and then included into flight planning?
When possible. Most of the time, the sensitivity regions are more applicable to G4 flights because they just sample over a larger area, and they do try and target those cold fronts, moisture gradients. And we work with a number of people. Ryan Torn at UAlbany also has a tool for identifying model sensitivity.
Okay.
Great. Any last questions? Well, please join me in thanking Kathryn again. That was very interesting. You're obviously doing lots of targeted research. Thank you.